Hello and welcome to the video presentation of Group 26 regarding application of knowledge-based control systems for the navigation of mobile robots, particularly with the focus on use of neural networks. The paper we were provided with as the basis of our literature review assignment was titled Neural Control System of a Mobile Robot. With that being said, let's get right to it. Mobile robots could play a significant role in places where it is impossible for humans to work, but they have also become more commonplace in commercial and industrial settings. This is a reason why their market size is projected to reach more than $50,000 million by 2026. Hospitals have been using autonomous mobile robots to move materials for many years, and more recently, warehouses have installed mobile robotic systems to efficiently move materials from stocking shelves to order fulfillment zones. In such harsh dynamic environments, learning and adaptation are very important features. Conventional approaches usually struggle with these aspects, and we will come back to why this is later. In this presentation, we will also discuss the use of neural networks, reinforcement learning, model predictive control, and fuzzy logic as more flexible, higher-speed control methods that are also capable of dealing with nonlinearities.
The problem of global navigation of a mobile robot can be divided into three main tasks, namely environmental recognition, local navigation, and global path planning. Environmental recognition concerns the conversion of sensory data to a map or subspace that the robot can use as an input for planning its motion in the next steps. Local navigation is how the robot decides its position and orientation in an online manner in order to avoid obstacles. This stage utilizes the subspaces created during environmental recognition. Contrary to local navigation, which assumes the current scope is in the vicinity of robot's position, global path planning considers the world as a whole and finds a suitable path towards the end goal. In a way, the global path planning portion of motion planning algorithms is the decision maker of the system. Mobile robot navigation has some challenges. Firstly, most conventional methods struggle with the recognition of obstacles because such methods show slow response due to serial processing of the data. Furthermore, conventional methods need great effort in programming to deal with nonlinear kinematics and dynamics of these robots. There is a difficulty of adapting to dynamic environments as traditional approaches are dependent on accurate metric description of the environment. Computational costs can also be a real issue in online obstacle avoidance applications, where quick responses are required. While neural networks can address most of these issues, they also struggle with certain aspects. They often require a significant learning phase. There might be difficulties with generalizing the neural network and also with preventing overfitting. And additionally, spatial inaccuracies of sensors and actuators also often limit the straightforward application of neural networks and other knowledge-based approaches. As a result, we have also investigated alternative knowledge-based control algorithms, which in many cases are applied in parallel with neural networks, as we will describe later. Let's first have a look at how neural networks can be utilized in mobile robot navigation. The authors of our main paper designed two environmental recognition neural networks, or ERNNs, based on discretely oriented distance measurements. The first one is designed and trained to recognize 7 standard subspaces such as a corridor, a crossroad, or a left corner, which represent the spaces that the robot could encounter. It contains 19 neurons for both input and hidden layers and 7 neurons on the output layer. In a similar fashion, the second environmental recognition neural network is trained to recognize 5 additional subspaces. In this paper, the approach to local navigation uses 3 neural controllers, namely a keep right, keep left, and a pass across road controller. These controllers, which were also able to define motion in the presence of unexpected obstacles, were trained by placing the mobile robot in 111 different positions. We shall now go through each section of mobile robot navigation, starting with environmental recognition. In addition to the ERNN described in the last slide, the second approach discussed here defines spaces in the following manner: a non-safety space, a safety space, and a free space. A cost function rewards moving from a proximal state to a distant state and punishes moving from a distant state to a proximal state. To this end, a Q-learning algorithm, which is a reinforcement learning algorithm described in more detail later in this presentation, is employed to help create a discrete state action decision map. A simpler approach can be employed by basing the environment on a deterministic grid map. When Q-learning is employed on this known map, the state action space becomes a deterministic and straightforward Q-learning problem. Unknown obstacles are found by detecting a grid occupation. A subsequent second best action is then chosen when the initial best action interferes with the object. As an example of a classic method, potential field navigation has also been considered. Here, obstacles are defined as repulsors and the goal is defined as an attractor. This generates a potential field which the robot can simply follow. However, it requires the obstacles to be mathematically modeled beforehand. As the problem of local navigation concerns the task of determining the required position and orientation in a fast and online fashion, we will now consider different approaches combined with neural networks that help achieve this task. The first combination of methods we consider is achieved through application of fuzzy logic to neural networks. Such a combination can address the speed control task in autonomous navigation. It's very difficult to control speed just by using neural networks alone due to the lack of experience for creating a training dataset. Additionally, fuzzy logic can be used in order to achieve obstacle avoidance. For this purpose, the outputs of a situation classifier neural network can be adapted in a fuzzy logic algorithm according to the 4 steps shown on the slide. For construction of the rule base, basic human reasoning can be used to generate an obstacle avoiding rule for each environment class. Such fuzzy rules can then be tuned by iterative simulation, for example using a genetic algorithm and the delta rule. Defuzzification of output variables for velocity and steering angles can then be achieved using the method of center of gravity. The second combination is neural networks and reinforcement learning. In a work from 2005, Q-learning was used in an online fashion to avoid obstacles. This variant of reinforcement learning can handle many state action pairs for obstacle avoidance, but it still relies on discretization of the sensed environment since it works with classic lookup tables. Therefore, the authors implemented a 3-layer backpropagating neural network to handle the large number of state action pairs. The network also allows for the interpolation of state action pairs that have not been visited. There is also a continuous variant in which Q-learning determines the weights of a neural network based on the reward obtained from the Q-learning algorithm. This approach is called neural Q-learning and is able to handle continuous state action descriptions. In this slide, we discuss the combination of neural networks and model-based predictive control. The first approach features an NPC to detect obstacles and to define a control input for the robot to move around the obstacles while closely following its global path. The NPC algorithm is able to compute a local trajectory to follow this global path. The problem is that for any realistic control horizon, NPC is computationally expensive. The authors here have solved this by training a neural network based on simulated data runs of the NPC algorithm. The neural network can now mimic the NPC at a fraction of the computational costs, thus proving to be efficient. The second approach discussed here is a neural predictive control for path tracking. Here, the state representing the position and the orientation of the robot from odometry measurements is estimated using an extended Kalman filter. The predicted state is computed from wavelet neural networks. In mathematics, a wavelet series is a representation of a square integrable function by a certain orthonormal series generated by a wavelet. Without going into too much detail about wavelet functions, the authors have proposed a wavelet neural network to compute the predicted state. Such a neural network is possible due to similarity between wavelet decomposition and the hidden layers in neural networks. When training the neural network, this approach can overcome the problem caused by the local minima. The error between the estimated state from the Kalman filter and the predicted state from the wavelet neural network determines the cost index which is used for optimal control of the robot. We also found 2 additional pure neural network approaches for local navigation. In the first approach, the authors trained a neural network with obstacles placed in different positions in front of a robot. This network learned how the robot had to turn depending on the position of the obstacle. However, it is cumbersome to train the network with multiple obstacle positions set manually. Another interesting approach is based on radial basis function. Here, training data is acquired based on the Euclidean norm distances from each obstacle. When a mobile robot approaches a set of distances from different obstacles, obstacle avoidance behavior is activated. This type of radial basis neural network is extensively used in autonomous navigation where the environment is unknown. Now we are going to discuss global path planning. In our main paper, the author presents two decision makers for global navigation. The first type concerns predefined path planning. Here, an expert specifies a series of subspaces and the direction in which the robot observes them. A neural network then recognizes these subspaces and local navigation can then guide the robot while avoiding unexpected obstacles. The second decision maker achieves autonomous global path planning. It computes the goal direction using sensors at the goal position and uses a neural network to check for existence of crossroads. A completely different approach is multi-hierarchical graph search, where the graph of a world is divided into different hierarchies. The authors define a search problem as a pyramid consisting of low-level rooms connected to high-level corridors inside higher-level buildings. When several problems need to be solved, the shared section of these pyramids only need to be solved once. This is the main advantage of this method. Finally, we found the distance transform path planner, which propagates a distance wave from the goal location back to the start. The shortest path is then the steepest descent one. This method requires that the environment is known beforehand to a certain extent. Let us now summarize the key points addressed in this presentation. First, combining with fuzzy logic, neural networks can easily incorporate human knowledge, giving rise to intelligent robots. Second, in combination with Q-learning, neural networks can handle complex domains. And finally, in combination with model-based predictive control, neural networks can help decrease the learning phase and reduce the computational cost. Thus, we conclude our presentation by saying that neural networks used in autonomous navigation can be enhanced when combined with other knowledge-based control strategies, giving rise to smarter navigating robots. Thank you very much for your attention and all the best.